in high school, you studied what we call the Hall effect. And this Hall effect ended up becoming giving rise to a Hall rod. And it was basically depending on the Hall rod is used to measure the magnetic flux density. And how it happened is that you chopped a semiconductor wafer. After chopping a semiconductor wafer, you had to put on its sides high resistance voltmeter, which you were going to use to measure the Hall voltage. And then you had to pass the current through this conductor. So I here was the conventional current. I'm just devoting the point. So you don't need to write. This was conventional current. You can either use this to mean our B, or you can basically draw the field lines to show how they are moving. Now, because of the existence of the current, the whole current, the current which is being transported by the positive charges is in this direction. But the electrons are meant to be moving in this direction. But using Fleming's left-hand rule, then if you made sure that the first finger then the second finger is for the current, and then the thumb is for the motion, or sometimes we say the force, but we utilize the M, capital M, the M for the motion. So if I place the first finger in the direction of the current, and then of the field, and then the second in the direction of the current, then these electrons will suffer a force that is upwards, so they will be deflected. Now that process continues as the current flows. Once you have switched off, the process continues until when all of the electrons are occupied the upper part, leaving the positives on the lower part. It's because of this potential gradient, or this separation of charges. I explained this sometime back using the dance floor kind of analogy. Then you get this small ball, and this happens when you have the magnetic force being the same as the electric force. And this is the BEV. This is the V, the drift velocity, or the velocity of the charges being the same as E. And then you can utilize the B, from also F is equal to BIL, you can get more variables and be able to get the whole voltage. Now, because here this is the potential gradient, which is the same as VH over D, or you can call it this distance between here, which is the, I say, thickness, and then you have this one as the length of the material. And this one you can call it maybe breadth. You can go on and on and get whatever you want. But all I'm trying to drive towards is that I'll be able to have the VH being the same as the BVD over I don't have any over. I can only get the over things when I substitute for the drift velocity from I equals to never. And then I can, and the A is the area, cross-sectional area, which is D, or you can have this as the thickness T, then you have it as dt, so you have I equals to never, after A is dt, and then you get your V, the velocity here, drift velocity of the charge is being the same as I, and then E dt, and then you can substitute it in there and get using those values. But that's not the issue. The issue is that even if you left it this way, you are able to get the whole voltage, and that whole voltage is corresponding to the amount of, or the strength of, the field that is existing in that one. So when you get the whole probe and you put it in a given region, you are able to determine the amount of or the strength of the field that you have. So we can use this principle to understand what we call the inductive transducers. So I will now go straight to the points. We gotta remember a couple of things before we do the. We have to recall some stuff. The resistant magnetism, and maybe somehow from electromagnetism, which we are covering. We shall talk about we have a electromotive force. Electromotive force. Correspondingly, in magnetism, we have the magnetomotive force. So the magnetomotive force, which we can abbreviate as MMF, let's have it as MMF is equal to the number of turns. If we are looking at a given coil, the number of turns times the current I. So I'll use small I for this purpose, for understanding this part. So this is I. Then the magnetic field intensity, just like you have the electric field intensity, magnetic field intensity is abbreviated or is given, denoted by H, and we shall find that H is the same as the force. It is an intensity, so it is this magnetomotive force divided by where this force is being felt, the region where it is being felt, all that region. So it will be the same as Ni, this magnetomotive force, divided by L. And the L is the path length in meters, where L is the path length in meters. And then we got the flux density, magnetic flux density. In electromagnetism, you obsessed with having it as B with and H and E and all this you have to make sure is they are vectorial. Here we don't bother about the direction. We are only interested in the effect. So the B is given by B is equal to mu H. And mu is the permeability. And this mu is the same as mu R, mu naught. And it is the permeability of free space, permeability of the material. Mu is the permeability. How permeable is the material to the magnetic fields? So this is permeability of the material. And then we got the mu R is called the relative permeability. The corresponding in electricity is the permittivity. And then mu naught has a value, is a constant, which is 4 pi times 10 to the power negative 7 on Rees per meter. And this is the permeability of free space. Permeability of free space. So I'm just doing a reminder so that the guys from Victoria don't have to curse me that they are talking about strange things. Now, whenever you have a bunch of magnetic field lines, and then these magnetic field lines are threading or are linking a given area, if you can get to calculate the amount of these field lines, being threaded threading this kind of area A, and they have the strength B or density B, then that linkage can be related with the area and the strength of the magnetic field. And then we say, or we call it the flux. So we need also to remember something to do with flux. The other one is B is flux density. This is flux. And flux, we denote it with capital phi, which is the same as the product of the area and the magnetic flux density. And we always focus on the area being perpendicular to the area. Sorry, the magnetic field lines being perpendicular to the area. And then we also talk about flux linkage, not leakage, linkage. I've had issues, students always writing leakage instead of linkage. It is linking, threading. When you have field lines threading a given material, going through a material, because field lines go through this metal. If I put a magnet underneath and I put a metal here, it will be attracted. So they don't care, they just go through wind, they are permeable to the paper, for example. So if I can denote this with lambda, then lambda is equal to the number of turns and then the flux. So you are looking at the magnetic flux linkage, you are looking at the number of turns and then times the flux. The field lines per unit area going through that area, the number of turns that you got. The geometry and the nature of the material, like the coil, brings about what we call the inductance. So the inductance L, we have that L is the same as lambda over the current I. So whenever we have a coil, and in that coil we pass a current, if we can make this current to, If we can make this current go on and off, then we can make it increase, decrease, and because of the resultant magnetic field lines or the magnetic fields behavior, eventually you get this coil itself having an induced EMF. The reason why we normally have the laminates in the transformer to avoid the induced current flow, which we call the eddy current. So then this would be the same as n squared over nice R, and that nice R is what we call the reluctance. So another term we shall meet is the nice R. Very nice R, but in the books you find it looking like Gothic handwriting, but I don't know how to write Gothic letters, unless if I'm looking at them. And this nice R, or this reluctance, is given by the L, the other length, of mu R, mu naught A. So we can compare the parameters in electrical part or in electric part or electrical part, and that in the magnetic part, so that we see if we use the Ohm's law analogy, how do we compare flux, what do we compare with flux, what do we compare with the magnetic linkage, so that we have to comparing electrical and magnetic, comparing electrical and magnetic variables using Ohm's analogy. Yields, we can put it in the form of a table. We have electrical part here, then we can have the magnetic part here. So I will start with the current, which we denote as I, and is measured in amps. Comparatively, we talk of this as flux, and which is in Webers. So I will put the wordings this side. We talk of the EMF, electromotive force, which is measured in volts. Comparatively, we talk of the MMF, or magnetomotive force, which we denote as F. Sometimes we say ampere turns, and this is the magnetomotive force. The other one is the resistance, and it's measured in ohms. Comparatively, we have the reluctance. So here we talk of the nice R, which is measured in ampere turns per Weber. And then we have this as, by name it is called reluctance. Finally, we need to have this material being able to conduct, so we talk about the conductivity, which has an abbreviation of sigma, and it is measured in Siemens per meter. On the other hand, the material should be able to be permeable. So comparatively, we talk of the permeability, which is measured on reads per meter, and then in words we call this permeability. So using the Ohm's analogy of V is equal to IR, and then when you go to the J is equal to sigma A, when you're interested in the current density, then you invoke the conductivity, and this is the microscopic form of Ohm's law. So this is how we can compare the magnetic variables of flux, magnetomotive force, reluctance, and permeability in relation to those we used. So when you are making a voltmeter or an ammeter, or you are having an ohmmeter, like we have our multimeters, we could use them, we were able to use them to measure the current, the same multimeter using it to measure the voltage, to measure the resistance, to confirm whether it is continuous using that diode gate. The same thing. You talk of the current, comparatively you are talking of the flux. You are looking at the electromotive force, here we talk of the magnetomotive force. We talk about the resistance this side, we talk of the reluctance of the material to be permeable to the current, the fields going through. And then the conductivity of the material is compared to the permeability of that material. And once we have known that, then we try now to see how, compared to the electrical things that we've already known about, then we can now try to relate and see what magnetomotive force, how magnetomotive force can be useful when we are trying to develop a transducer. So, just like we said, the electromotive force drives the current through the circuit, the magnetomotive force NMF drives flux phi through the magnetic circuit of reluctance, nice R. It's very interesting to write this R. So MMF is equal to the flux times the reluctance. But we say somewhere, I wrote the damn thing, that the MMF is the same as the product of the current and number of turns. So the number of turns and the current would be the same as the flux times the noise, times the reluctance. So from now I no longer say nice R, I will say the reluctance. So, and if we really were to compare with our electrical part, this would be the way of saying that E is equal to I, no more resistance R. So here where I is the current, which is producing the three lines, and the number of turns, And then nice R is the reluctance. Phi here, from here we would have phi is equal to Ni over R. If we have only one, what would happen? I over nice R over reluctance. So we have the definition. Self-inductance is the total flux per unit current, and that means that we have that the inductance is the same as phi over, or we would have that L is equal to N squared over nice R. But we have that R, nice R, is equal to L over mu R. Okay, it should be mu times the area, where mu is mu R times mu naught, where A is the cross-sectional area and L, I've already said, is the total length of the flux path. And then mu naught, I've already defined the mu naught and the mu R. And we can say that the magnetomotive force is sometimes called the magnetic pressure. Just like we sometimes call voltage the electric pressure. So we've talked about magnetic circuits. So what are examples of magnetic circuits? Of magnetic circuits. So we can have a simple magnetic circuit like the one of, if we just had one set of windings of coils on the transformer. So if I had a current source, okay, coming to the primer of the transformer, and then I have a couple of windings, and then I have this current here flowing in this direction. Then I will create the magnetic field lines. These field lines I will move. So these dotted lines are the magnetic field lines which have been created. And in order to know the direction of these field lines, I just need to grab the coil and curve my fingers in the direction of the current. So this current comes like this, goes behind, comes here, goes behind, comes here, goes behind, comes here, goes behind, and completes the circle. So the field lines will be in the direction of my thumb after curving the fingers in the direction of the current. So the field lines will be in this direction. Then complete another one here, going this way, coming down, going this way, going down here. So we can have this as A. This is when we have a complete path. So if we put anything here, if we connected our secondary windings here, then we would be able to get the current in if we had either a galvanometer here, we would be able to register the current, sense some current or some voltage. But also if we tried to have chop off this part, if we chopped off this part, and left the gap there, and got an armature or got the material, ferromagnetic material, and put it here, it would also feel the magnetic fields which would be coming from this place here. So I still have my coil here. I have the current source. This is the current. Then I will be having the current in this direction, and then I will have the field lines going across and interacting with this other material on the other side. And then I can have another set, just to have two of them. And then still using the fingers now, I should have drawn it like above, but now I drew it in a different way so that the field lines will be moving in this direction. I just did it intentionally to make sure that you don't think that that's how it has to be drawn always. So if this gap is an air gap here, we have an air gap here. And if we call this our setup or our circuit B, the presence of the air gap causes a large increase. Causes a large increase. So what would increase here? Our terminology is, we have many terminology. We have flux density, we have field density, we have reluctance, we have... so what would increase here when we now introduce the gap? The field lines will now find difficulty to cross here. Yes, they will cross because the space, free space is permeable. But compared to mu air being equal to 1, the mu naught is 4 pi times 10 to the power negative 7. You see, it is very small compared to the air. Is 1. I mean, air is 4 pi times 10 to the power negative 7. If you chose to have the free space is 4 pi times 10 to the power negative 7. But then now that is what you have. So if you have a material like either iron or steel, whichever magnetic material you have, it will be higher than what you have for air. So it would have been easier to make these field lines cross. Now when you put an air gap, then it means that you are introducing or you are trying to increase our noise which is the reluctance. So this causes a large increase in the circuit. The circuit reluctance, and the corresponding decrease and a corresponding decrease in the flux, because we said that not long ago we said that the flux is the same as Ni over I over R. So if you, that is for a single term. Now if you have for n terms, then you have phi equals to Ni over R. So if you increase the what you are dividing to, then it means you are decreasing what? So the decrease in flux, and we also said that L is the same as phi over R, and or we can have it as N squared over R. We are increasing R, so will be the inductance. We have two types of inductances. We have mutual and self. Self is what you think about and you become high. Mutual is what is around you that makes you high. Either way, you get high. From these simple circuits that if you were to be able to chop up that part and create a gap, you'd interfere with the reluctance. And when you interfere with the reluctance, you can change the flux. Then you can change also the inductance. And the flux, thinking from Faraday's law, it is all about flux. For example, that if you have your flux, and then the induced EMF is proportional to the rate of change of flux. Now, if you can do this, that means you can change the induced EMF. If you can try either to increase or reduce the flux, so you can change the value of the induced EMF. And then if you can do that, then you can create sensitivity, and then you will need this. You have created a sensor. Where is sensitivity? You create sensor. Anything that feels any sensitivity is equally a sensor. So let's look at a variable reluctance. Variable reluctance displaced sensor. Or you can call it transducer. The two are synonyms. So if we had a semi-toroid, the toroid is if you got a solenoid and then you make it into a coil, then you would have made a toroid. A solenoid is a coil for which the length of this coil is greater than 10 times the diameter. Any coil where its length is about 10 times the diameter qualifies to be a solenoid. If you got okay, assuming we have this, and then we have created, we have passed through our current. Let me just create this. So I have created a magnetic field to the second, not the second, there is no second response, but this is my my core. Preferably, you have to use a sluggish material like iron. Iron is easily cooled, easily charged. So, for example, iron core. So, what do you think is the permeability of iron? We know the permeability of free space is the same as 4 pi times 10 to the power negative 7. It is, sure, it is very, 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 very small. So, but then, so that means I'm sure the one of iron, for example, if I can use Fe for iron, is way greater than 1. I'm very sure about that. Magnetic material, its permeability is greater than 1. So if you chop this part, here, and make this armature, this material, which we are calling an armature, just nearby, it means that for the field lines to cross, they have to cross this air gap here of mu naught. So the magnetic threading now means what we call reluctance. They are not focused to the other material the way they will be moving in the whole core. So they reach the air gap, some of them will start now diverging because you have this current here from this current source moving in this direction, you create almost a bar magnet. So the field lines, when they reach here, they start. If this is the north, they start diverging just like a bar magnet. And then here they also start coming in again on the south part in a divergent way. So there you create the reluctance. That's what it means by that air gap creating reluctance. And then they have to again collect again and start moving through. So you have lost this part, lost this part, lost this part, lost this part, and then these direct ones try at least to make sure they can survive across this other armature. So I was still saying that if you have a coil whose length is 10 times the diameter, or is more than 10 times the diameter, we call that, we no longer call it a coil, but now if you get a good one that you are able to now make it a coil. So for example, you are able to make it become a coil on its own. It's a coil, and again you make it a coil. Then you make what we call toroid. I'm not sure whether it is double D or single. Double R or single. Is it double or single? I'll go with the double until the further notice. So if I was to have a semi-toroid, so I have half a toroid, I will draw a line and make it be neighboring to an armature. So I will make the I'll just put these few, but which shows that they are supposed to be, the whole half should be, having the windings. So if I will have the field along this semi-toroid, and I can have this part to show the distance from the toroid, semi-toroid to the, so if this is our D, the air gap, Now, when we have an air gap, basically we cannot assume that the permeability is 4 pi. Normally when we talk of air, we end up having the permeability being equal to, you sometimes when they say the material is not magnetic, is not, because free space is actually when you have no gases, nothing. So you tend to have this graph having the relative permittivity being equal to 1. And then if we took this to have a cross-sectional area, cross-sectional area and radius small r, and if we took this to be the center of our semitoroid and take this to be the radius capital R, not the reluctance but the radius. So this is our core, because this is the toroid, the coil, but this is the core. Like iron, you have iron which is, made nicely where the coil is rolled. This is an armature. And this core has relative permeability mu RC. So if this is our sensor, it consists of 3 parts. The sensor consists of 3 parts. It has a semitoroid or semitoroidal part, semitoroid. 2, this gap here can be changed by moving the armature. That is the variable air gap. And then the ferromagnetic plate, which we are calling the armature. So the key point here in our sensor is about the reluctance, because reluctance affects the flux, and the flux affects the induced EMF, or simply call it in a new sense our magnetomotive force. So the total reluctance of the total reluctance of the magnetic circuit is nice R total equaling to nice R of this core here plus the nice R or the reluctance of the armature plus the reluctance of the air gap. So in order not to confuse air gap and the armature, we used the A, so we can use A and G for purposes of, because we, at the end of the day, we have mu R C, we have, this should be mu R A, so mu R D, but we said that that is equal to 1, so we are not going to be using it. So what was the definition of reluctance? Some time back, I told you what was R equal to in terms of the relative permittivity, the permeability, and when we did the free space, what was the reluctance in terms of mu R, mu naught, the length of the path, and the area of the cross-sectional area of the flux linkage over. So let's now work out the. So for the core, what would be the length? What would be the length of the core? It's a semi-toroid, it's a semicircle, so, and it is of radius capital R, so we would be having pi over mu R, but this is mu R of the core, then mu naught, and then what would be the area? The area now is the cross-sectional area of the core. So that would be pi small R squared. The armature, this other stuff here. So I drew it in 2 dimensions, but basic, and this one I drew it in 3 dimensions because I showed this part. So basically, this armature is like this, and it should be having the cross-sectional area also, and so what is the length of our armature that is interacting with the field? Because the field is, this is actually the direction of the field. The field comes down like this. You can have some arrow. So what is the part of the armature that actually interacts with the field? What is its length? 2R. So we have 2R divided by mu RA for the armature, mu naught, and then what would be the area? You chop a donut, you slice a donut into twice, so I have my one part of the donut, let me draw it a bit like I used to go and this one I can't shade. So we have this part, and then we have the thickness T here. So definitely we shall have, I can't, assuming that this is our 2D, and then this is cast on this other part here. So the whole of this part here, so 2R. So this is 2R. Is the part that is cast, and then when this field line is linked, the armature and starts streaming through towards the other side. Our T here, so the cross-sectional area, the one we are having as 2R. So T is thickness of the armature, and I guess I no longer have any problems. So if I factorize out, so now I have an R also, okay? So when I have an R, I will now put one of the other is outside, so it will be 1 over mu RC, and then R plus 1 over, then so I have mu R and then capital R, and then small r is already outside, so I'll have a T, and then I add, I can still continue, add on the 2D of 100 remains, but to remove the R which I would have brought in, and I will be having pi R. Okay, so then I can reconfigure it. Any problems? This one here. Okay, I don't know why I cancelled it. So I don't have the R. I only have a T. Okay, so this would be total. I'm sure you will not forget this thing, because we have done it together. So this would be, I don't know whether it can come, but you will not. And then we have A 1 over mu RCR plus 1 over mu RNT, then plus, I want to regain it again. It will be 2D over mu naught by small r squared. My reason of doing that is that this one now gets a new baptism as the R, the reluctance R naught, which is the same as reluctance at 0 air gap. At 0 when you have the armature touching the torus. Thus, our total reluctance will be equal to the reluctance at 0 air gap, then plus KD, where K is the same as 2 over mu naught pi r squared. I've just replaced this 2 over this as a k. So assuming that most of the flux in the armature is concentrated in the area, in our cross-sectional area of the armature, which is 2R RT. So therefore, self-inductance is given by L is equal to n squared over reluctance, which is equal to n squared over reluctance with no air gap plus KB, which is the same as L naught over 1 plus alpha D, where L naught is the same as n squared over R naught. Okay, nice R naught, and the new new constant alpha is K over reluctance with 0 air gap. And the new constant we've brought in, alpha, depends on the geometry. Permeability, to mention by you. Now, although the inductance is nonlinear, with respect to D, this is with respect to D, you do this one in integration. We use the differential push-pull displacement sensor. We use the push-pull displacement sensor. I think we also did talk about this tactic in the capacitive transducer, and we were able to mention it, and then we should be able to move on to this differential displacement sensor, just like we had capacitors. Just like we had plates for the capacitive solid transducer. I don't know why reluctance is in my head. We shall also have our two circuits, our two magnetic circuits. And then have the other magnetic circuit on the bottom here. So we can have L1 here, L2 here, and then if this is our middle line, we can have our armature AB, and if these are at a distance twice D, and we have displaced them at X, then we would be having this being a middle line, this is D. So the whole of this now would be D plus, and this one would be D minus X. And then we can work out the inductances L1 and L2, integrate them into our AC bridge, and then get the V out in our bridge, and be able to get the value of how our sensor will be working. So if we could have anything that is moving within between the circuits, the AB, the armature AB, and then we will be able to get these two values, and then now it will give us the reading. We shall do that on Wednesday.